Melissa is the co-founder and lead researcher of Off-Planet Research, is a provider of Lunar Regolith simulants for testing and research purposes. This goes exactly to what Dr. Veda just said a moment ago. We need to figure out how to live off the land. Off-Planet Research is a private research company that strives to enable a meaningful, enduring human presence beyond Earth orbit by helping organizations learn how to work and live on the Moon, Mars, and other worlds safely and productively. They produce high-quality simulants, test materials that emulate the regoliths and ices of the Moon and other planetary bodies. They also design, adapt, and test components and processes for inclusion in future missions. These resources dramatically increase mission assurance, cost effectiveness, and speed of development of safe and effective space-based technologies. Melissa is a member of the LEAG Lunar something group. I don't remember what LEAG stands for. LEAG Commercial Advisory Board, and a leader for LSIC's Extreme Environment Regolith Survey Interface Group. Thanks, Melissa. Join us, please.
Of course, yeah, no, I also thought that that was a great transition there at the end. How wonderful. So let me go ahead and pull up my presentation real quick. Okay, well, thank you so much. My name is Melissa Roth, and I am one of the founders and lead researchers at Off-Planet Research, located in Washington State. And I want to thank the Moon Society for having me today. It's exciting to be back. I will be speaking about the formation of Lunar Regolith, the challenges that it presents to human and robotic missions, and how Lunar Regolith and the resources within it can be leveraged to help sustain a long-term presence on the Moon and in deeper space. So a little bit about us. Off-Planet Research simulates extraterrestrial environments for testing spacecraft and landed technology with a current focus on the lunar environment. As engineers, we know how testing and good test materials are important to increase that mission assurance, cost effectiveness, and speed the development of space-based technologies. OPR was founded in 2015, and we spent several years developing our Lunar Regolith simulant production methods, make sure that we mimic the natural formation processes on the Moon, as most commercial crushing equipment tends to smooth the particles or contribute high levels of contamination. In addition to our Lunar Regolith simulants, we have also developed Lunar Icy Regolith simulants that include the 9 L-Cross components found in the L-Cross flume. Additionally, we consult on working with Lunar Regolith and conducting component testing. The prevailing theory of the origin of our Moon centers around a giant impact that threw off material that eventually formed the Moon, with both planetary bodies now at a little bit of a tilt. Returned Apollo samples support this collision theory as well. When you look at the Moon, you can see the light and the dark patches. When Galileo looked at the Moon through a telescope in 1609, he thought that the dark patches looked like the smooth bodies of water, so he called them Mare, an Italian word for ocean. When he studied the lighter portions of the Moon, they looked rugged like the mountains on Earth, so he called them the Highlands. These are the names that we actually still use to this day. The soil in the darker colored Mare is mostly composed of basalt, as seen in the photo here on the left of our Mare simulant. Basalt is most commonly found all over Earth. However, some terrestrial basalts are a better match to lunar basalts than others. The simulant on the right is representative of the lighter Highland areas, which are mostly made up of rocks called anorthosite. A Chian anorthosite is not very common on Earth and is more than 3.5 billion years old. When the Earth was cooling down from a ball of molten rock, this anorthosite was one of the first components that solidified and floated up to the surface. Now, when you were looking at that photo of the Moon, I imagine that the image on the left is the one that comes to mind for most of you. What many people do not realize is how different the far side of the Moon looks. There are a very few Mare patches on the far side of the Moon, and while the lunar highlands cover almost 80% of the lunar surface, most lunar missions have actually landed in the Mare regions. And due to challenges with the Earth and the far side, only one mission has landed there, which is Chang'e 4. To clarify some terminology, regolith is the term that we use to refer to the layer of consolidated rocky material covering bedrock and is used to describe the soil on the moon and other planetary bodies. Lunar regolith simulants are the materials made here on Earth to simulate or replicate the regolith found on the moon to be used in research and testing due to the scarcity and protection of returned lunar samples. The environment on the moon is one of the most challenging that humanity has ever encountered. In addition to the extreme temperatures of plus or minus 260 degrees Fahrenheit, one of the most difficult parts of this environment is the nature of the regolith on the moon. Earth's soil contains organic material, and the particles are formed by wind-blown and water processes, which makes them relatively round and smooth. The regolith on airless bodies, such as the moon, have no organics, are not altered by moisture, and are entirely formed by impact and explosive processes. This means that these particles are very hard and covered in fractured surfaces, with sharp edges, as in that image in the middle. The regolith on the moon is very destructive and hazardous to both humans and technology. It is abrasive like sandpaper and also very susceptible to static charge due to its high surface area. Additionally, more than 60% of the regolith on the moon is composed of particles that are quite fine, like those in talcum powder or cake flour. Due to all of these factors, regolith particles easily get into the spacesuit joints or moving mechanisms of rovers and cause them to seize up. Considering how short their missions were, astronauts' gloves and suits suffered a lot of damage. The Earth is fortunate to be protected from most meteors by our atmosphere. Those that do get through radically change the landscape, like in that upper photo, which shows Meteor Crater in Arizona. The moon has no atmosphere, so even tiny micrometeorites hit the surface, making their own craters that behave just like their larger relatives. This is how rocks on the lunar surface get crushed into a very fine powder. Additionally, the energy of the impacts melts some of the surrounding regolith, which quickly cools and glues other regolith particles together, forming agglutinates, as you can see in that lower left photo. Due to the structure of agglutinates, they have a significant effect on the mechanical properties of lunar regolith. In this iconic photo of Buzz Aldrin on the left, you will note just how white his suit is, with the exception of a couple of dark spots on his knees from a fall. On the right, James Irwin's bottom half is absolutely coated in dark gray regolith. Not only is the regolith abrasive and destructive to the fabrics and joints, but the astronauts were susceptible to overheating, as that pristine white design was meant to help reflect heat. And I do just want to note how difficult it is, or how dangerous it is for astronauts like Buzz to fall, and yet he was not the only one to do so. Given the nature of the regolith and rocks, falling into this sharp abrasive material could ruin the suit and put the mission and the astronaut's life at risk, especially if they are not near a lander or habitat. The ability of the astronauts to move freely and safely while wearing a suit cannot be overlooked. Fortunately, I know there are some new suit designs out there, and I look forward to seeing how they enable astronauts to get more mobility, but also how they hold up to that regolith. A new dust-generating system arrived on the moon, starting with Apollo 15 in the form of the Lunar Roving Vehicle. While the LRVs dramatically increased the distance traveled and mission capabilities, they also stirred up even more lunar dust to coat the LRV, the astronauts, and their instruments. In regards to cleaning the suits after each EVA, Gene Cernan said, "Probably the most difficult job of all the closeouts was trying to dust the suits." In the photo on the right, a very dirty Gene Cernan can be seen in the lunar module after taking off his suit. What I find fascinating about this photo is that Gene should have been protected from the regolith in his EVA suit. His skin was never exposed to regolith outside the lunar module. The suits being dirty makes sense, the astronauts inside them less so. And despite all that time spent cleaning, as we can see, the regolith that did enter the lunar module quickly dispersed around the cabin. Many astronauts developed lunar hay fever as a result of breathing in these fine abrasive particles. In fact, researchers are now studying how long-term exposure to lunar dust might affect the lungs of future astronauts. This table shows some of the statistics of the Apollo EVAs. The 6 missions over 3.5 years show a rapid advancement in the amount of time spent outside the lunar module, the total distance traveled, and the quantity of samples brought back. The addition of the lunar roving vehicle drastically increased the distance covered by Apollo astronauts, and thus the variety of samples brought back. That said, the longest the astronauts have spent on the lunar surface is less than 24 hours. So if the dust was so abrasive that it wore through 3 layers of the Kevlar-like material on Jack Schmidt's boots, how will our technology survive weeks to months on the lunar surface? If you're attending this conference, you know that many national space agencies and private organizations have visions for a long-term sustainable presence on the moon and in deeper space. With almost 50 years since the last human mission to the moon, how can we make these visions a reality? As I'm sure has already been discussed, NASA's solution is the Artemis program, a series of missions with the goal of landing the first woman and the next man on the moon by 2024. The first phase of this ambitious program begins with smaller landed missions, transitions to larger landers with deployable rovers, and is going to culminate in a crewed mission to the lunar South Pole in 2024. The second phase will build upon the first to increase mission capabilities for Mars. There are also many other missions planned through international collaboration and private industry, such as Chang'e 6, the Emirates lunar mission, and Luna 27, to name a few. While normally industry struggles with bridging the gap between technology and business, while still applicable for the space industry, the bigger struggle is about bridging the gap between technology designed for environments on Earth and technology and designed for the moon and other worlds, of which we often have incomplete or little knowledge. These unknowns are called strategic knowledge gaps, or SKGs. They are questions that researchers and industry experts try to answer or plan to answer through a mission. One such knowledge gap is dust mitigation. As I mentioned earlier, Apollo-era technology had many issues operating in dusty environments on the lunar surface, and they just kind of had to live with it. Well, for that vision of humans inhabiting the moon, you can't just live with the dust. We either need to prevent dust from collecting on surfaces in the first place, or we need to create new technology that is more durable for this harsh environment. So first, let's look at some Apollo-era dust mitigation strategies and see how they did. In addition to procedural mitigation techniques, cleaning processes, and strict planning to avoid hazards, astronauts use dust brushes, dust covers, and rover fenders to reduce or remove dust. Now, the problem with a brush is that it often creates static. As I mentioned earlier, with particles that are very fine and susceptible to static charge, these brushes were really only marginally effective. Additionally, what happens when a vital component breaks on the moon and the closest hardware store is 239,000 miles away? There were actually several instances of life and mission-threatening breaks during the Apollo missions, but one almost prevented the final 2 lunar roving EVAs of the Apollo era. At the end of the first Apollo 17 EVA, Gene Cernan's hammer caught on the edge of the fender and it popped off. Without that fender extension protecting them from the dust, driving the LRV was a serious hazard. Due to the 16G, any lofted dust goes much further than it would on Earth, and they described it as driving around with massive rooster tails behind them. This lofted dust spread all over instruments and suits, and since it's darker than the instruments or the astronauts' bright white suits, it absorbed heat from the sun and could overheat the instruments. So while the astronauts slept, the team in Houston had to create a replacement fender with only the materials the astronauts had on them on the moon. Their solution was to attach 4 of the 28 lunar maps with duct tape and 2 telescope alignment clamps, as seen in that middle photo. This amazing story illustrates the importance of thinking on your feet, adapting technology, and learning from experience how to mitigate dust. Without this fix, the only geologists to set foot on the moon might not have had the opportunity to discover the orange glassy regolith on the edge of Shorty Crater during that second EVA. With missions launching soon, both nationally and internationally, new dust mitigation techniques are needed. We need optical systems such as camera lenses, solar panels, and spacesuit visors. We need advanced fabrics for spacesuits, habitats, and covers. Thermal radiators and painted surfaces will help with heat reduction. Dust-tolerant mechanisms like linear actuators, bearings, rotary joints, hinges, and quick disconnects are all necessary for technology longevity. New seals and soft goods for spacesuit interfaces, hatches, connectors, and hoses are going to be very susceptible to abrasion. So going back to that vision of a lunar village, we've studied the environment, we've developed new dust mitigation techniques that work great, and we're launching missions on a regular basis. Wonderful. Well, now we need to address the business case that we set aside earlier. Science and research goals can only fund so many missions. Governments can only fund so many missions. It would be hard to make the case for a lunar or Martian village without being able to show the financials of why we need to go and not just why we want to go. This is where lunar resources come into play. We need to be able to show that the resources of the moon, Mars, and asteroids can literally propel ourselves deeper into space. This all starts with the idea of in-situ resource utilization, or ISRU. ISRU being the idea of living off the land and utilizing the resources around you. There are so many resources that can be extracted from the regolith and used on the lunar surface. Lunar regolith is at least 40% oxygen by mass, and silicate minerals make up over 90% of the moon. There are a variety of metals and crete components, that's potassium, rare earth elements, and phosphorus in the regolith as well. Volatiles refers to the frozen components that have been discovered in lunar ice. In the 2009 LCROSS mission, NASA crashed a satellite into the South Pole and discovered water, carbon dioxide, ammonia, and methane, to name a few, in that ejecta plume. LCROSS estimated 5.5 weight% of water in addition to the other volatiles, while spectral modeling estimates up to 30 weight% ice. With one data point of ground truth, there are a lot of unknowns for volatiles, but they have really revolutionized how lunar resources can be used. The oxygen and hydrogen can be used in rocket fuel, breathable air, drinking water, and in agriculture. The rare earth elements that are in their unrefined state on the moon can be exported back to Earth to be used in many applications like electronics. Raw or processed lunar regolith can be used in sintering and 3D printing applications to make tools and construct buildings, protective thermal and impact shields, and roads. Earlier, I mentioned that there are a lot of unknowns about the volatiles found in the lunar polar regions. The largest supply of volatiles that is most easily accessible from the surface is expected to be in the permanently shadowed regions where the sunlight never hits. These regions at the North and South Pole are often in or at the edge of craters and are ultra cold at minus 260 degrees Fahrenheit, or even colder in certain craters. Early missions to the polar regions will send prospecting instruments and rovers like NASA's Viper rover to head into these extreme access environments to categorize and map the distribution of volatiles in preparation for future excavation and extraction missions. Later missions will then utilize these resources to create robust infrastructure on the lunar surface. So back to the business case. In order for ISRU, and particularly lunar rocket fuel, to make sense financially, it needs to be less expensive to source propellant from the moon than to launch it from Earth, and there needs to be a market. With the recent flurry of mission planning to the moon and deeper space by the commercial industry and national and international government agencies, the market has mostly been defined. The biggest delta V is getting out of Earth's atmosphere. Once you're out of LEO, the delta V significantly reduces and each kilogram of propellant is more efficient. If the cost of propellant obtained from the moon in LEO is less than the cost to ship propellant to LEO from Earth, the business case can be closed. Refueling upper stages in LEO to transport heavy payloads from LEO to GEO and beyond. This can increase the affordability of NASA's activities on the moon, ESA's Moon Village, and missions to Mars. While the savings depend on the in-space transportation approach and assumptions, there is now a big business case that can be made for sourcing propellant in space. In fact, a 2019 WGM report has released a conceptual economic study on mining water on the moon. They see the market as encompassing satellite refueling, the International Space Station and Lunar Gateway, Moon and Mars bases, space agriculture, tourism, and hotels. They are valuing this market at $206 billion over the next 30 years. The moon is a stepping stone to the rest of the universe, but it should not be overlooked for the science and resources it offers in its own right. By developing lunar resources, colonizing space becomes profitable and desirable. Regolith, which is one of the biggest nuisances and hazards of the moon, might just be the very reason humanity can envision a thriving economy in space. Ultimately, the reason for becoming a multi-planet civilization is to better the lives of everyone and ensure the survival of humanity. As we begin the next stage of space development, we need to ensure that we work to make this vision a reality while not repeating the errors of our past. And learning to survive and thrive on the moon is our first step towards this new existence. In the future, there will be thousands of people working and living to space. So here's to the beginning of the next great human adventure. Thank you for your time, and I welcome any questions.
Thank you, Melissa. Always terrific to hear you. So without being a jerk about this, regolith is difficult to deal with, yeah?
Yes, we can tell you even the terrestrial stuff is not the most fun, but you know, learning how to utilize it here and kind of some of the nuances will hopefully help influence decisions and technology that can be used on the moon. So we got to do it, right?
I want you to tell us a little bit of inside baseball. You know, you have worked with these materials for a couple of years. You just moved laboratories just recently. Tell us about some of the surprise stories of your own experiences in your own lab. Like you've worn down equipment that you thought was going to last for a long time. Tell us some of that stuff, please.
Definitely. So basalt, I think a lot of people are very familiar with. It's very porous. Believe it or not, it's softer than the anorthosite. The anorthosite is really hard. It has a lot of crystals in it. And so just looking between the two and how we have to crush them down, and the output that they produce has been very eye-opening. Additionally, as you mentioned, when we started refining our processes and getting closer and closer to the final processes we wanted to use, we were breaking our equipment. We had, nuts snap off. We had glass jars that we had put material in with, a lid, and the lid we wouldn't be able to turn it because it had kind of seized up from the particles that got into those grooves and kind of jam themselves in with their little angular abrasive surfaces. So kind of learning, to make sure the top of the jar is clean, which is something that, makes sense. But in a laboratory environment, you're just sealing a jar, right? Well, no, you're not just sealing a jar. So kind of things like that. What sort of materials do we need to use? How often do we need to replace them? It's fascinating how quickly metal as well abrades away in the presence of these materials. So we're utilizing all of that, and we're excited to be able to share it with clients who are looking for that sort of expertise.
Well, and it's challenging to just function with this stuff in your own, one atmosphere environment, right? So imagine what it's going to be like to keep an environment clean when you're out in the middle of it, right? Like, how do you do that?
Definitely. I mean, I think about how much the dust lofts here on Earth, and that's going to be nothing compared to how much it lofts on the moon, because it really does like to spread around, get everywhere. It finds those little nooks and crannies to hide in, and it's very interesting. But that's again where we need to develop dust mitigation techniques, and honestly, an array of them, and probably combine that array of them. We need more tolerant materials. We need more tolerant designs that aren't going to allow the dust to collect as much, that are going to help the dust, kind of fall off, so to speak. And then obviously we need some removal procedures as well. The brushes weren't the greatest, so what else can we use? Are there cases where we do need brushes? If so, what style and design is going to be more effective? So that's where I think that it's going to be some very interesting work over the next few years.
Dr. Veda was referencing an Antarctic style station. I have a hunch that an Antarctic style station would be the tippy top of luxury as compared to a lunar settlement. The earliest lunar settlement is going to be a mess, I think. And I really think it's an underappreciated problem And so testing in advance, is pretty darn important and certainly mission critical. Um, I know that you've recently won a couple awards. Can you talk about them publicly or not just yet?
Yeah, so one of our grants is from the National Science Foundation, and in that grant, we're expanding our IC regolith capabilities to be able to make the process more portable and also size it up a little bit. It's great if folks want to come up to beautiful Seattle, at least when we're not in a heat wave. But we recognize that not everyone can, that they need to be able to test remotely at their facilities or elsewhere. And so it was really important to us to be able to make that process portable. And at ultra cold temperatures with some corrosive gases, it's not quite as linear as you might expect to size that up and do it elsewhere. Additionally, we had a NASA phase 1 SBIR to start answering some of these questions about dust mitigation. We were looking specifically at fluid and gas connectors to operate repeatedly in dusty environments.
Food and gas connectors?
Fluid and gas.
Fluid and gas, okay.
Yeah. And really looking at, for long-term missions, whether they're robotic or human, you're going to be able to need to reuse components multiple times in dusty environments. They're going to get regolith in them. They might be dropped. And so what can you do to design hardware that's going to be more durable for that environment?
I'm going to ask one question. You only have about 2 minutes to answer it. How does mammoth capacity of Starship change your vision of the future, specifically your business model for off-planet research?
Yeah, so I guess I should ask the question, are you envisioning Starship on the moon or Starship for Mars?
Well, I'm aiming definitely for the moon. Definitely for the moon. Sorry, that's a bias of mine.
Okay, us too, at least for now. No, I think the interesting thing about Starship is just that, honestly, the mass that it can take up is going to be so much more than we've been anticipating. So add in the years of trying to reduce mass, reduce volume. Hopefully we'll be able to get a lot on the ships. Additionally, hopefully it will allow us to bring things that can then make more on the moon. So when you're looking at, as someone in the comments mentioned, 3D printing, or you're looking at space agriculture or building habitats, you're going to need, in all likelihood, composites or even some water to kind of create the mixtures or the cements, essentially, that you're going to need. And so being able to bring up some of those resources is going to exponentially allow more to be made on the moon, especially if we're smart about what goes up on what mission, to really help build that infrastructure. So as you mentioned, those first settlements might be a little rough, but what is going to be needed? Do we need what sort of equipment, what sort of tools, what sort of, again, kind of composites or additives? How is the regolith going to be used? How are we going to sift it? Do we need to sift it? All great questions.
Terrific. I mean, I think it's a fascinating future that we're going to be building together. So, good luck to you and Vince and the rest of your team. We're going to shift over to our next speaker. Thanks a lot, Melissa.